Hi, I'm Andrew. I'm one of the TAs for the lab course you're taking right now. So I'm here to talk to you about what is Lab 11, or torque. So I'm going to go ahead and write that down, torque. Okay. So the concepts that we're trying to cover today, we're going to talk about extended free body diagrams. We've been doing a lot of work with just regular old free body diagrams, all the points, all the forces acting from a single point. And we're going to talk about the differences between those kinds of free body diagrams and the extended ones. What else are we going to talk about? We're going to talk about torque about a pivot. Now what does that mean? Okay, so when you're dealing with torque, you generally have a force acting at some distance from a pivot point. And we're going to dig into a little bit about how to find that torque and a couple of different techniques to understand that. Once we have a good understanding of what torque is, we're going to go into torque balancing. And what that means is that will help us solve for unknowns in a given system that we might not know what forces are acting where. So we're going to go about torque balancing to find unknowns. So those are the general concepts that we're going to try and talk about today in the lab, and I guess we'll get right into it. So we want to look at what is torque. So just let's go ahead and answer that question real quickly. What is torque? Torque's a bit of a confusing topic for most people, including myself, to try and teach, but we're going to try and draw from an analogy. If you were to try and get an object to move, you would apply a force to it, right? So your force is equal to mass times acceleration. If you wanted to get an object to rotate, then you would apply a torque to it, much like you would apply a force to an object just to get it to move translationally. So let's make the analogy that torque is equal to this weird letter I times angular acceleration. Now this I is the equivalent to mass, where we're going to say that for the sake of this, I is how hard it is to get something to start rotating, just like mass is how hard it is to get something moving. And then A is pretty simple. The acceleration is just going to be the acceleration. This is angular acceleration, and this is your standard acceleration that we pretty much understand. And then this is your moment of inertia, and this is your mass. So really these two are related, and those two are related. But moving on from there, the other way to find out what torque is, because this is just a way to think about torque. This is what it actually means. It means if given the moment of inertia of an object, or how hard it is to get it spinning, and you know the torque, you can find how fast it's starting to spin up. But then, in order to find out what torque is acting on an object, it might sometimes be easier to look at it as torque is defined as the force that's perpendicular, that means perpendicular, acting at some distance d. So what does it mean to be a force that's perpendicular? So for instance, we're going to go ahead and draw a board, right? If we act with this on this board, we'll say this is the pivot point, right? So this is your pivot right there. Then this right here would be our distance d, okay? So at this point, let's say we have a force acting perpendicular to it, and that's going to be F1. So in order to find the torque acting about this pivot point, we're going to multiply this force, which is already perpendicular to this distance, right? It's 90 from that, if we could just draw that, and now we understand that this is 90 degrees from that board. Now, that would just be, our torque acting at this is just force 1 times the distance. Okay, does that make sense? I'm going to just ask that question. You're going to say yes, because you get to watch the video over and over and over again until you get it. Great. Now, the next thing that we're going to deal with is torques that aren't, or forces that aren't necessarily perpendicular to the board, right? Because we do get that. We sometimes have that happen. So if this is your pivot point again, we're going to say that's the pivot. And I'm going to say, let's say this force is acting that way now. So this is force 2. All right. So we can't really just say torque is equal to force 2 times the distance, right? And I'll go ahead and label this as the distance. So there's your distance. We can't say torque equals to F2 times d. We can't say that because this is acting, the magnitude of that force is not quite perpendicular to the board, right? So what do? You might have seen that torque is defined as Fd sine theta. Now, what does that mean? Well, that's going to tell us that if we have a board, I'm going to go ahead and draw this again. We have a board and a force, right? Here's the pivot. Here's the distance d. Okay? And this is what we're going to call that force 2 again. Well, this then is going to be our theta. And the reason that is because I'm going to go ahead and draw, let's see, I'm going to draw this triangle here. Okay? So this is theta as well. So we're trying to find the component of this force, force 2, that is perpendicular to the board. And that will be defined as F2 and then sine times sine theta. And that makes sense because this whole line's force 2, that's the hypotenuse. This is the opposite side that we're interested in, and that's theta. So the perpendicular component of the force is then just F2 sine theta. So much like the situation that we had before where it was where our force was acting perpendicular, we could say F1 sine theta is equal to force 1 perpendicular. But because theta is 90, F1 sine 90 is just equal to F1. So that, in short, that's just a way of saying force 1, all of the force of force 1 is acting perpendicular to the board. So that then brings us back to this side where we're dealing with this torque at an angle. So that then tells us that the torque acting around this is force 2 perpendicular, which is force 2 sine theta, times the distance that it acts at. All right, so this is the torque acting around this this system, this pivot point right here. So that covers what torque is, and that's on our list of things that's torque about a pivot. So we kind of skipped the extended free body diagram for a second just to get an understanding of what torque is. So let's go ahead and move on to what a extended free body diagram is. So let's say we're given a situation where we have someone standing on a board. Let's go ahead and draw a diving board. Okay, so this diving board's held perpendicular to the ground, and now we have a person standing on it. Okay, well now he's sitting on it. Okay, so this person is sitting at some distance right here. This is distance d, and he is acting with a force. We're going to say this is force due to gravity, and we're going to just call that force 1. All right, so in this system, we've got a couple of different things to keep in mind. We've got force acting down where the man's sitting. We've got the center of mass of the board, so that would be another force that we have to take into account. And then we also have a force holding the board up at this point, at the pivot point. So let's forgo the center of mass for now. Just let's talk about the two forces here, the one acting up here and the one acting down here. So an extended free body diagram of this is going to be a simplified picture, but with the forces acting at these points. Otherwise, if we were just drawing a regular free body diagram, this would simply be a normal force. Would be considered the normal force. And then we would have the weight of the man, and these should be equal because it's not moving, but I kind of drew it off. And that would just be Fg. And then these would cancel each other out. But for the sake of studying torque, we need an extended free body diagram where we include the fact that there is some distance, d. So then we go ahead and draw that we have a force holding this up. And this is going to be the same length here as what we would have expected in our free body diagram. And that's a normal force. And then where this weight is acting. Okay? So that would be force due to gravity. Now, this right here then tells us that we're producing a torque. So, if we're trying to find the total torque around this extended free body diagram, we are going to then, total torque is equal to, well, it's just simply all of the torques that we have going on. So force I, N, and then D, I. So this is a fancy way of saying torque about this point plus torque about that point is equal to our total torque. So if we choose our pivot point smartly, we can get rid of one of these torques. So there's a torque 1 here, and there's a torque 2 here. But if we choose the torque such that this D is 0, so we say that this point is 0, we get force 1, the normal force, times its distance. Well, that distance is 0, plus force due to gravity times its distance, which would be distance d. So then we could say the total torque is just Fg times the distance. Now, I did kind of skip over the fact that this is supposed to be perpendicular, but because it's acting perpendicular in our situation, these two statements are the same. Now, what if we had a more complicated system? I'm just going to go ahead and draw one out for us and say, let's say we have an oddly shaped thing. And we had some force acting here. This is force 1. This is force 2. This is force 3. And then let's say this is force 4. And then we wanted to find out the torque about this point. Well, we would have to do a couple of different things. We'd have to find out the distances between these. I'm going to go ahead and draw a couple of lines here. Make sure that they're straight. So here we go. There's a line here, and a line here, and a line here. This is going to get messy for a little bit, but hopefully we can keep up with it. Okay, so at each of these points there's an angle involved, right? So this one right here, we'll go ahead and say that this is theta, this is theta, and then this is theta. But we also notice here, this one right here, that's theta equal to 180. Well, this then would tell us that if theta is equal to 180, force 4 sine theta, its theta, is force 4 sine 180, and that is just equal to 0. So that tells us that there's no torque, and that makes sense because if we're pulling straight away from an object, we're not putting any rotational, there's no need for it to start rotating because it's not trying to be pushed in a direction that would make it rotate. So the torque about this pivot point produced from F4 is 0. So then the other things, we should probably label these. These are theta 1, theta 2, theta 3, and then theta 4. So this would be theta 4. Theta 4 being 180. So then, if we wanted to find out all these torques then, so the total torque, T-tote, or tau-tote, is equal to force 1 sine theta 1. And then we also kind of have to pay attention to that, the distance, d1, plus force 3 sine theta 3, and then d3 times d3 plus plus force 2 sine theta 2 d2. All right. So this is a bit tricky though, because I've actually drawn all of these such that they're all positive. Let's say we have a force that acts this way. This acts in the opposite direction. These three forces, force 1 and force 2 and force 3, all produce a torque that would make this object want to spin clockwise actually, right? So if we're going clockwise in the physics world, clockwise is actually the negative direction. Clockwise is defined to be negative. It's a bit confusing, but it has to do with the fact that in math we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. You might have seen that before, and that just tells us the direction of rotation around a set of axes. So this then is the positive direction, so that we see that counterclockwise is actually positive. So really then, these all are negatives, but that's okay. We just know that this one's acting opposite to these ones, so then we're going to then just say, let's say this is F5 now, line here, and then that's theta 5, D5. So since this one's fighting the total forces or the total torques acting this way, we then will add another term saying F5 sine theta 5, and that's just the perpendicular component of the force acting at distance 5. So then we multiply this by d5. That would be the total torque acting around this silly looking extended free body diagram. Okay, so that takes care of, so we've done, what have we talked about? We've talked about torque about a pivot, we've talked about extended free body diagrams, and now we need to talk about torque balancing to find unknowns. So in a situation where we have, let's see here, another piece of paper. In a situation where we have an unknown force, let's say we know that there is a force acting here, force 1, and that one's perpendicular. For the sake of just simplicity, I'm going to make all these forces perpendicular, right? So and then we have a force 2 here, and we know that there's a force acting here, but we don't know exactly how big it is, right? And we then want to know what this torque is acting around, or what the force here is based on the torques that are being placed at this point. So there's a couple things that we want to look at to make sure that we understand what to do. So this right here, we'll call that distance 1. And this right here we'll call distance 2. And then this little bit right here we have to also keep track of, and that's going to be distance 3. So then we'll say this is force 3, but we still don't know it. So in our list of variables, force 1, we know. Force 2, we also know. D1, we know. D2, we know. We also know D3. Okay, and then force 3 is what we're looking for. Okay. So let's put a little question mark there. In order to find the total net torque acting about this object, we have to take into a couple things into account. We have to state that this is not rotating, right? Cool. So, given the way this is drawn, force 3, at least from here, is going to produce a positive torque, or a negative torque, my apologies. Negative is counterclockwise, or clockwise. These all produce clockwise torques. Now, force 3 is indicated to be positive in the upward direction. Force 1 is going to be considered positive in the downwards direction, and F2 is also positive in the downward direction. We're just basing this off of the fact that they're all rotating around this center point. So that's going to come into play a little bit later. We're going to see something funny about force 3 that we didn't necessarily expect, but what we're going to do then is say force 1 times distance 1 plus force 2 times distance 2 plus force 3, and we got to remember this is our unknown. Go ahead and draw this in red maybe, or underline it in red. And then times distance 3. This is all equal to 0 because there's no net force acting on it. So what we do then is we try to solve for F3. So what we're going to do is we'll subtract F3, put it onto the other side, so we get force 1, D1 plus force 2, D2 equals negative force 3, D3. So then the only thing left that we have to do is divide out D3, so we get the total torque from force 2 and force 1 divided by the distance that this force is acting at. And that tells us that it's negative F3. So in order for us to then figure out this force here, we notice that it's negative, and that's because of how we defined these values. If it's not moving, then a force that's acting in the positive direction around this point would just add to it. So really what we're looking at then is a force that is acting downwards to fight the forces acting this way. I hope that makes a little bit of sense, but that's just telling us that this force here, force 3, is the opposite direction that we were expecting it to be. And that's where this negative shows up at. I'll go ahead and circle that in red. That's where that negative comes from. Okay? So other than that, this is kind of the situation that we would do. We add torque 1 to torque 2 to torque 3 and set that equal to 0. And that is the basis that we start with. And then as we go along, we can start to get the variable that we're looking for onto one side on its own, and then once that's done, we have an equation that tells us exactly what we're looking for. Now that covers the last bit of this talk, so then I'm just going to end it there. Thank you very much.